All right, we're set. Okay. Well, thanks everyone for attending. I guess it's our third Zoom seminar series. We appreciate all the support, and if there's anyone that's interested in speaking at one of these in the future, please let us know. We're always looking for new people, and it's a good way to kind of spread the word what our users can do, and we get ideas from each other. And I think this is a good thing that Arena came up with, and it's benefiting all of us. Today, I'd like to introduce Kevin Dalton. He's a postdoctoral fellow from the Department of Molecular and Cellular Biology at Harvard. He works with Professor Hekstra at Harvard, and Kevin has been a regular user at BioCars for several years now, and working with electric field experiments. Kevin's talk is titled Variational Bayesian Merging for Crystallography. It's all yours, Kevin.
All right. Oh, I'm not being allowed to share my screen.
Uh-oh.
Okay. Did you fix it, or you would like me to fix it?
No, I did not.
Okay, let me do it. Oh, you have to do it because I cannot.
Oh, I started the session?
You started the session, yeah, you have to do it.
All right.
Click on him, right click, and give him a privileges.
All right, I think you're set, Kevin.
Try.
Can confirm. Yeah, everything looks good.
Okay.
There we go. Good.
Okay. Well, first off, thanks for inviting me to give this talk. It's nice to have to see so many of the BioCars community here. I feel like I've spent a lot of time at BioCars, but I haven't really interacted with too many of the folks who use the facility regularly. So this is neat. What I'm going to talk about today is what has essentially been my quarantine project. This started in earnest in February and really has kind of taken off since then, especially since I transitioned to working remotely in mid-March. And the idea behind it is to use these tools from contemporary Bayesian literature in order to improve merging of crystallographic data, and not just Lowy data. This is a totally general principle that I'm going to be talking about, and it works well with both conventional and Excel data as well as Lowy. And so to outline the talk, I'm going to spend the bulk of it describing the algorithm that's behind the code. And the way we're going to do that is first I'll just remind everybody about data reduction and crystallography and how that goes. And I'll pay particular attention to kind of the last step of data reduction that most people don't think about all that often, which is French-Wilson scaling, because I really view this algorithm as French-Wilson's kind of spiritual successor. And then I'll introduce my algorithm. And I want to emphasize right now that while this is a pretty fully featured merging package that I've written, it's really should be thought of as just a proof of concept. It's going to be improved a lot by including more thoughtful physical models in the future. What we have right now is pretty generic. So it is useful. I can't recommend it for general use cases, but I think for time result and Lowy applications, it might be ready to go. And I'll talk about a couple examples. So one would be conventional merging and scaling of a SAD data set. And then I'll talk about a Lowy time resolved data set. And we can talk about, do some conclusions and wrap up afterwards. Okay, so crystallographic data reduction will be familiar to most of you all. This is the general workflow. First, you have to infer the orientation of the sample, by which I mean the A matrix of the crystal that generated the bright spots in each image. And then you typically do some sort of geometry refinement where you refine the geometric parameters of the experiment so that you can better predict the locations of Bragg peaks on the detector. Then you go and visit all those predicted spots and you integrate them, and either by summation or profile fitting. There are a number of ways to do that, number of different algorithms. And then once you've gone and collected all those spots, right, we have this scaling problem in crystallography, and that's due to the fact that every time you observe a Bragg peak on the detector, you really only get a fraction of its true theoretical intensity, and the particular fraction that you get, varies throughout the data set. And so we have to do what's called scaling and inflate all the intensities throughout the data set by their appropriate amount in order to average them parsimoniously together. Okay, and so then once you have the scaled intensities, you merge them. This is usually just done by a simple maximum likelihood kind of averaging routine. And then you're left with an issue at this point in terms of data reduction, right? You have intensities that you've averaged, but due to systematic errors throughout the data set, it could be the case that some of these intensities are negative. And that may not seem like such an issue, but when you consider the fact that the structure factor amplitudes you want, your map coefficients that you want, and at the end of the day, in order to compute electron density are proportional to the square root of those intensities, you end up with an issue, right? You can't take the square root of a negative number and be left with a totally real argument. So that's a problem that was solved in 1978 by French and Wilson. And their algorithm, the idea behind it was, let's use our prior knowledge about the expected distributions of structure factor amplitudes in order to update our intensity measurements so that they're strictly positive, and again, that they follow those expected statistical distributions. So this is a Bayesian algorithm. It uses a prior, and it computes this so-called Bayesian integral. Can everybody see my mouse, by the way? Just want to double check.
I don't see it.
You don't see my mouse.
Every once in a while, now I do.
Okay, I'll turn on the laser pointer then. Okay, thanks, Rob. Yeah, so the idea is to use this Bayesian integral to update our measured intensities to be strictly positive. Okay, and the way that works is, well, this thing that we're computing is the mean of the posterior distribution over this latent variable j, to put it in Bayesian terms. But what it really is the expected value of the true intensity. And this integral is simply an expectation over j that's weighted by a normally distributed error model that's centered around the empirically observed intensity, and it's informed by a prior distribution. Okay, so this is the normal error model that I was referring to, and the model in French and Wilson says that I_OBS is drawn from some distribution around our latent variable j that's got a sigma, a standard deviation, a scale that's congruent with the empirically estimated uncertainty. Okay, so this is an empirically estimated uncertainty. This is I_OBS, this is sig I_OBS. Right, and this prior distribution that French and Wilson used was the original Wilson, AJC Wilson's prior distributions from way back in like 1949, I want to say. And you get to these distributions just by thinking, okay, what if my unit cell just had like randomly distributed atoms? There are different formulations of this for the centric and acentric reflections, but that's really just a detail. The important thing to know is that they're parameterized by this. Both of them are parameterized by this capital sigma here. And what that is the mean intensity, the average intensity in each resolution bin in the reciprocal space. Okay, so in the French-Wilson algorithm, they had to come up with a way to estimate sigma in a resolution-dependent way. Luckily, when you collect a crystallography data set, you get an enormous amount of data. So the solution back in 1978 or whatever it was to just to stratify the data into resolution bins and take the average intensity and plug that in for these priors when computing this integral. And the integral was computed in two different ways, depending on whether you're centric or acentric. It turns out if you're an acentric reflection, there's actually a closed form, an analytical form of this integral, which is pretty easy to compute. So that's what was done then, and it's still what's done today. And then for the centric reflections, that integral turns out to be a little bit more challenging. So way back when French and Wilson tabulated the results for that integral using numeric integration as a function of sigma and the intensity J. So that's just a table that's written down in their supplement, and it's still the same table that gets used today under the hood every time you run Phoenix to do French-Wilson scaling. All right. So my thought is, like, let's take this idea of estimating nice positive structure factors that follow Wilson's priors and just extend its reach further up this chain of data analysis steps. So what if we, instead of going through integration, scaling, merging, and then French-Wilson scaling, what if we just applied the same concept to the raw unmerged intensities, unmerged unscaled intensities? So that's what the algorithm is all about. It's about using this modern Bayesian tool called variational inference to apply the French-Wilson idea directly to unmerged intensities. And I've called this thing careless, obviously as an homage to Phil Evans' famous aimless package for merging conventional X-ray data. It's open source. It's up on GitHub. And like I said, what it does is it takes unmerged intensities in the form of an MTZ and gives you merged structure factor amplitudes. And along the way, it does this by learning two things. The two objects it learns are the mean and standard deviation of the structure of each structure factor, and it also learns this this sort of scale function. In our case, the scale function right now is parameterized by a neural network, but you could imagine using other sorts of machine learning models down the line. Okay, and this I'll get into in more detail later, but the idea behind the scale function is that it takes metadata about the reflection and outputs the appropriate scale that they need to be corrected by. And to be more specific about how it works, what it really is at its core is in my mind a probabilistic forward model of diffraction. So we're using Bayesian machine learning in order to predict the intensity of each reflection in a data set, and then we fit the model to that to try to repredict the data. It uses variational inference, as I mentioned, which is kind of a contemporary and approximate inference method in the Bayesian literature. What that means is, instead of computing an integral or computing an integral like analytically as French and Wilson did, or computing an integral by Markov chain Monte Carlo, which is the other major method in the Bayesian literature, you use optimization under the assumption of some particular parametric form of your posterior in order to do the inference problem. And I'll be very, very specific about what that means in context through, in the next handful of slides here. The way I have implemented it, this uses automatic differentiation from TensorFlow, so we don't have to do any tricky calculus. And it uses these reparameterized distributions from the TensorFlow probability library. These are super cool. This was a major result in the Bayesian teens, like 2013, 2014. But you can use this so-called reparameterization trick in order to include the sampling operation, kind of Bayesian sampling operation as a number in your computational graph. And that means that you can compute gradients, you can propagate gradients through the sampling operation into the underlying parameters of the distribution. This was huge. It's enabled a whole lot of neat machine learning. And we're just taking advantage of the fact that now it's widely available in these open source libraries. Okay, so this is what the underlying model in Careless looks like. I'm going to walk through this because I imagine some of you are probably not super familiar with these sorts of probabilistic graphical models and how to parse this. But basically what you need to know is that the gray circles, those are your data. Those are things you observed in the experiment. Any of the empty circles, those are distributions that you're trying to learn. So they're random variables with a full distribution, usually parameterized in some way associated with them. And then these little black circles they're things you are going to learn during inference, but they are not like the empty circles. They're not full distributions. They're not random variables. These are just going to be scalar point estimates. So like I said, this particular gray circle here is representing the observed intensity. This big mess of spiderweb business is the neural network that we're going to learn that does the scale operation. So it ingests the reflection metadata. So these are just facts about each reflection observation. I'll be more concrete about that as we go on, but it ingests reflection metadata and it outputs two things. So it goes from the dimensionality of your metadata down to 2. And the things that outputs are a mean and a standard deviation. Those are used as the parameters of the scale factor distribution here. So it goes from kind of RD to R2, and then you use these things to build up a normal distribution. You sample from that, and down the line. We'll be a little bit more concrete as we go on, like I said. And then the final thing that we're trying to learn here is this structure factors, FH, should be relatively familiar to people. All right, so that thing was a lot to look at. So I'm just going to collapse the neural network. We're going to use this reduced representation. It's totally equivalent to the previous representation, but just takes up less space and it's less jarring to look at. We'll keep this guy around for the remainder of the talk. All right, so what I'm going to describe now is the particular kind of like ideal Bayesian parameterization of this model that Careless is trying to implement, because this probabilistic graphical model here doesn't really tell you about the particular forms of the distributions that need to go with each of these nodes. It really just tells you the conditional dependence of all the variables in the model. So it tells you how to compute like a joint probability, but it doesn't tell you how you should parameterize each of the nodes. So we're going to go through the parameterization that Careless uses. Okay, so like I said, the neural network here, it takes a metadata vector, it outputs a mean and a standard deviation. And then for each reflection observation, you have a normal distribution. And we sample the appropriate scale factor for that observation from this normal distribution. That's the output of the neural network. And I've been a little bit opaque about what I mean by metadata that the neural network ingests, but this is exactly what I'm talking about. Here's a like pretty run-of-the-mill MTZ that came out of dials. I would say that the vast majority of the columns in here are actually not what I would call data per se. I refer to data as the integrated intensities and their corresponding error estimates. And all of the other stuff is kind of metadata. It tells you facts about the reflection, but it doesn't tell you the value that you integrated or any idea of the distribution of values which might underlie it. But in principle, you should be able to use all the information in this table to come up with an appropriate model to predict the scale that a given reflection is And then of course, like we said, we want the structure factors to be pulled out of some appropriate distribution for crystallography. In this case, we're going to go with the Wilson distribution, just like French and Wilson did. You can write them down in a scale independent way as well as the scale dependent way that that French and Wilson used. And that just looks like this. You say that for a given structure factor amplitude, it should be drawn if it's centric from a half normal distribution and if it's eccentric from a radial distribution. And these are, of course, parameterized by this little epsilon here, which is just the multiplicity of the reflection. It's a feature of the space group. It's different for each Miller index, or can be different. And it's just a number, it's just an integer that you can look up in a table. So it's just bookkeeping, really. It's not something we need to learn or anything like that. All right, and then we have a protocol written down over here already for how to get a scale for each reflection observation. We have a way to get a structure factor amplitude. And so if we just use the fact that the intensity is proportional to the square of the structure factor, we can write down that the IOP should be equal to the scale times the structure factor amplitude squared. All right, and then we're going to build an error model around that concept so that this is like a predicted value for each intensity in the data set. And we're going to assert that a given reflection observation should be drawn from a distribution centered at this predicted value. And again, just as French and Wilson did, it's going to have a standard deviation that's determined by the empirical uncertainty as measured in the experiment. Okay, so using this, we can write down the log likelihood of the data given the model. And if we were doing it, aside from one caveat, which I'll explain in a minute, if we were doing exact inference, MCMC or something like that, at this point we'd be done. We could sample this and come up with estimates for the posterior distribution over each of the structure factor amplitudes. But because we don't have a prior yet on the parameters inside the neural network, it's kind of a non-starter. We can't do that. And I would say, neural networks are famously opaque. So it's difficult to go and write down what we think is the sensible prior on them without just arbitrarily choosing one. So what we're going to do is we're going to switch to a different paradigm, and we're going to avoid thinking about what is ultimately a hard problem. Trying to come up with a good prior on these parameters and here is hard to do. Now, even if you could come up with a good prior, the data are going to be pretty high dimensional. When you solve a crystal structure, you usually have to estimate 10 or 100,000 structure factor amplitudes, and that's just too much to do exact inference on with contemporary computing resources. I mean, it's close. You could probably do it. I mean, people do, like, for instance, phylogenetic trees by Bayesian inference. Now you can get up to a couple thousand taxa, and you could probably do it. It would take a really long time. It'd be way too expensive for an experiment like this for anybody to actually want to do it. That being said, even if you decided you were going to devote the compute resources to it, what you would be left with at the end of the day is some kind of like wonderful exact posterior over structure factor amplitudes that would be totally non-parametric, and it could have all sorts of weird features. It could be multimodal, be asymmetric, be all kinds of crazy things. If you were handed that object, you would have no way to tell Phoenix what to do with it. So it's kind of a waste of effort at the end of the day, in my opinion, at least, until we have a way to tell refinement software, like, here's this really complicated posterior over structure factors, right? Now that may change. I know people are working really hard on this on this stuff, trying to make refinement, take advantage of more information. So we may get there, but right now it's kind of a waste of effort. So what we're going to do instead of exact inference is we're going to use what's called variational inference. As I mentioned, we're going to evolve the variational approximation for this Bayesian model, and we are going to allow the parameters inside the neural network to be optimization variables. Likewise, we're going to choose a distribution of parameterized structure factor amplitudes. We're going to allow those parameters to be optimization variables as well. And we're going to fit a loss function. Okay. So when you're evolving a variational approximation, the first thing you want to do is pick the variables that you're interested in, that you want posterior estimates of. In this case, that's going to be structure factor amplitudes, right? And then we're going to choose an appropriate variational distribution to approximate its posterior. So we want to think about, when we're doing this, what sort of distribution is going to be useful in capturing the features of the posterior. And in this case, the most important things are that we're going to have the same support as the prior, so 0 to infinity. And all we care about, because I already mentioned about Phoenix, all we care about is really getting the first and second moments right. So we want a 2-parameter distribution, most likely, that has the right support. So what we use is in Careless is this truncated normal distribution. Just a normal distribution that's been chopped off at 0, and it gets rescaled appropriately as density falls below 0. And here's where the sleight of hand and variational inference comes in. What we're going to do from a modeling perspective is take our original correct exact Bayesian model, and we're going to take the draw from our prior and we're going to swap it out. So we're going to switch the variational distribution for the prior distribution. And then in order to learn this thing, what you do is maximize this function, okay, which is called the evidence lower bound. And it's quite simply, it's the expected log likelihood of the data minus the Kullback-Leibler divergence between the variational distribution and the prior distribution. And we learn this with respect to the variational parameters. So the location and scale parameters of those truncated normal distributions, one for each structure factor amplitude. And we kind of just allow the neural network parameters to float in order to best maximize this likelihood. So the 2 terms I mentioned, right, it's the log likelihood, or the expected log likelihood in this case, of the data given the model. And this just assures that the model is actually going to faithfully reproduce the data that we measured. And then the second one, this KL div, all it does is encourage the variational distribution to look like the prior distribution. So if you are familiar with optimization and you've done like regularized maximum likelihood before, this is basically the same thing. This is basically like a souped up regularized maximum likelihood model with a very particular regularizer that comes from arguments in the Bayesian nature. Okay, so that's pretty much it for the model. I want to pause now, and because I just went through a whole lot of math, I want to pause and make sure that people are still like relatively with me and see if we have any questions. So is everyone good then?
I think we're good. I'd say go ahead.
Cool, awesome. I'll move on then. All right, so like I said, this is kind of a forward model of the diffraction problem from stats instead of physics. And I want to explain to you guys why I think this is like a really powerful way to do data reduction. Forward modeling is good, that's what I'm going to argue. And the example I'm going to use, everyone will be familiar with this here, which is an issue that happens when you collect Lowy data which is that because of the spectral nature of the beam, you end up with a diffracting condition bounded by these two limiting spheres in reciprocal space, and this third resolution sphere, so wavelength spheres, and then the resolution of the data inherent. The result of this is that every reciprocal lattice point that lies on the same central ray in the reciprocal space is going to end up getting the exact same scattered beam wave vector. And what that leads to is the reflections end up exactly superposed on the detector. So you have multiple different wavelengths contributing to the same spot and exciting different Miller indices, different Bragg peaks. And the traditional way to deal with this is to set up a whole bunch of linear systems and solve them. And I think Drumren is here actually. This is like the classic paper. I think about this, and this was like really seminal work. I think it really extended the reach of Lowy to especially getting good completeness at lower resolution. Turns out this sort of problem is actually much easier to deal with in the forward modeling kind of paradigm. So all we have to do to deal with this in our code base is to take the original model, and instead of making this draw from the error distribution a function of a single predicted reflection, all we have to do is sum all of the predictions that lie on a particular ray. So all we have to do is replace the center of this predicted distribution with a sum over a small finite number of predictions. And to implement this for me, it took about 100 lines of code, and it's really like mostly comments, if I'm being honest. So all I had to do was swap out the likelihood for one that ran a sum over each central ray, which I thought was really like a pleasant surprise. Because to be honest, when I first started developing this code, I wasn't thinking about Lowy at all. I was thinking about XFL data. And so to be able to quickly implement harmonic deconvolution, or as I call it, harmonic convolution and sort of forward modeling, was just a huge boon and something that was totally unexpected. So I explained in great detail the model, but it's not any good if it doesn't actually work. So I wanted to go through just a couple of quick examples and also introduce the command line syntax for running the code. So the first example I want to talk about is a life design room temperature sulfur SAD data set. This was collected at sector 24. It's 1,440 images, 6.5 keV. As many of you will know, lysosine has 4 disulfides and 2 mets. And we integrated this data in dials, where in this case we used Jack Reisman. We integrated this data, I should say. And again, this is what the reflection table coming out of dials looks like. So command line interface for Careless is pretty simple. You just call the program, tell it whether you're doing mono or poly, so monochromatic or Lowy. And then you have the option of a bunch of flags. For instance, in this case, we told it not to merge Friedel mates. And we asked for 100,000 gradient steps during our loss function fitting. And then the interesting part, you get to tell it all of the metadata columns in your MTZ that you want the neural network to know about in order to compute the appropriate scale for each reflection observation. And then it's just input file name and output file base. This is what the training trajectory looked like for this particular model. It took order of probably a couple of hours, 2 to 3 hours to fit this model and do cross validation and things like that. So it's not fast by like aimless standards yet, but it's getting there. I'll explain that a little bit more. Okay, but after processing and merging in Careless, we were able to get these pretty nice anomalous difference maps We saw, signal above 10 sigma for each of the 4 disulfides and for the 2 meds as well. So that was very encouraging early validation that this could work pretty generally. Since then, so this was kind of state of the art back in September. Since then, I've made a bunch of improvements over the last month or so. They're all kind of like boring implementation particulars, but they matter quite a lot. So one thing is I was very careful about improving the numerical stability and making sure that, like, really down to machine precision, all of the distributions have the same exact support. And also went through and messed around with the initialization of the variational distributions and the neural network. And the upshot of this is, at the end of all this optimization that I went and did, I was able to get models that converge now, like in 10x fewer gradient steps. So we're starting to get to where we might be competitive with more conventional merging softwares, which is really enticing for me. And one big thing is, like, I made a slight error the first time that I implemented the loss function in Careless, and so changing that really improved the accuracy of the software. And after doing that, I was able to get, like, very high resolution, high quality SAD solutions for this data set, which I was not able to do before. So I was able to get robust anomalous signal in terms of a difference map, but I was not able to leverage it to get a SAD solution. And now I get SAD solutions with, like, if you all are familiar with AutoSol, it gives, like, 0.45, 0.43 regime figure of merits for the quality of the experimental phases. So this is still in my experimental branch. I'm going to push it to GitHub in probably 2 weeks. So if you want to go and try out this code, I would urge you strongly to just wait a couple weeks. But it should be ready to go once that hits the main branch. So the second example, probably more interesting for this audience, is the time resolved PYP data set. So this is kind of the gold standard system for time resolved crystallography. This is the data that Letitia uses in the biocars workshop. And as most of you will know, PYP undergoes this light-induced isomerization, transistor isomerization. The data we have are off versus 2 millisecond post-laser time delay, and 20 images for each data set. I'm betting a lot of you have seen these images before. So 20 images each, often, and 2 milliseconds, 6 pulses, X-ray pulses per image. And again, Jack Reisman integrated these data for me in precognition. Take the output from integration and precognition and merge it in Careless right now. So this is what the precognition output gives you, right? Gives you intensity and an error estimate. It's a pretty Spartan reflection table, but it has everything you need in order to process this stuff. Most importantly, the wavelength. Obviously, you need that to do wavelength normalization. All right, so the call signature for running the polychromatic branch is, pretty identical. I added some extra stuff here. I added an I over sigma cutoff. This is incidentally the default learning rate for the gradient descent algorithm, so this is superfluous. Oh, importantly, if you're doing time resolve, there's this separate files flag, which takes every input MTZ that you give it and keeps them separate for the purposes of output. So what this is saying is scale them together, but merge them separately in principle. Yeah, I think that's all I need to say about that. And so running this on that PYP data gave me a pretty nice difference map. If you choose the parameters correctly and spend the time to optimize them to get the most signal out of the data, you can get a difference map that looks something like this. I would emphasize that this this is a completely unweighted difference map. So this is just the direct output of careless without applying any weights during the FT. Okay, I guess we'll wrap up now. So the conclusion is, I think for this audience, this is the only open source Lowy merging package that I'm aware of at the moment that supports both wavelength normalization and harmonic deconvolution. So if you want to merge your Lowy data, I think this is the only open source game in town at the moment, but you will still need to prepare your data and most likely in precognition or something. Yeah, I don't know what other groups use. Right, it's pretty flexible. It's easy to write new modules, scaling modules and things like that. It'd be interesting to start collaborating with some other developers and sort of reifying their physical ideas about merging and scaling inside of Careless. That'd be neat. It really does make it pretty easy to do things with scaling that you might not be able to do with other packages. And I believe I've shown that it's sensitive enough to be useful. And with that, I just like to throw in some acknowledgements. I've got to thank Duca's group. Thank Duca, of course, for giving me a lot of advice, introducing me to this full world of Lowy crystallography. And Jack, I've worked with extensively on this project, and he has written his own sort of, well, I should say we've written it together, a separate data analysis package that's for general purpose crystallographic data analysis that's available on GitHub. It's called Reciprocal Spaceship. And Ian and John are two students in the group who have been really helpful. I've had a lot of conversations with them about variational inference, kind of my go-to guys for advice about Bayesian stuff. I got to thank Wikita and Rob especially, and I should have put Irina on here for inviting me to talk. We've collaborated extensively on this project and others with the Mariathan Lab, and Igor is our go-to guy at AnyCat. So yeah, thanks. And I guess at this point we can take questions.
Thanks, Kevin.
Yeah.
Great talk.
Thank you.
And I guess usually we clap at this point. I'm not sure how that works under Zoom. But the floor is open for questions. Anybody have anything? Question? I was wondering, are you using this for your electric field work at all then, or do you see that being?
We haven't just yet, but we'll start using it very shortly here. Like I said, I developed it mostly for analyzing free electron laser data, so that's my use case for it. But I think in the lab we'll transition to using this for merging time resolved Lowy data pretty soon here, because it has this nice global scaling model, right, where you can take both your on and your off data and all of your time points if you want, and you apply the exact same scaling operations. So it's powerful in that way in terms of pulling out faint signals.
Oh, great, wonderful.
I have a question. Actually, two. So the first question is a clarification question. So in your first example for lysozyme, you said you collected data at 6.5 keV, and then you were talking about anomalous signal. Can you explain whether like two different wavelengths, or it was polychromatic beam? Can you explain?
This was a conventional data set, so monochromatic. Yeah, collected at AnyCat on a Dectris detector. So just like pretty routine crystallography, excepting that it was at room temp. Yeah, and a single wavelength. So the SAT experiment.
And how you can see what is sulfur? I'm not a crystallographer, so maybe that's very stupid question. So
okay. Yeah, actually, it turns out that if you collect enough data, you can use some prior beliefs to break the ambiguity about phases.
Can you say it a little bit loud, because your voice is a kind of fluctuates, so I can't really hear your full sentence.
Oh, I'm sorry. Maybe this is better. I think my microphone's like up here. This is better. So
yes.
Yeah, there's software out there. You can do this in Phoenix. It turns out that you don't really need to collect multi-wavelength data to solve the phase problem for most data sets.
Okay,
again,
then
I'm not the expert on that. That'd be like Tom Terwilliger, I think.
Okay, then my second question is, quite a while ago, we collected at BioCars data sets for small molecule. So it was a small photoactive molecule in a single crystal, pump probe. But we were never able to analyze the data set because, you know, of some issues with the software. So the software was written by one group, and, you know, there was also transfer of knowledge in that group. So basically, we have a very old data set which we never were able to process. But my question to you is your software suitable for small molecule or only for proteins or large molecules?
I have never tried to run it on small molecule data, but as far as I know, it should be. It supports all space groups, all of the ones that are whatever the like 500 and some odd like settings that CCP4 also supports. So it should get all the particulars right, as far as I know. It'd be interesting to try it. I don't know what concerns there are when it comes to merging small molecule Lowy data, because I imagine your Bragg peaks are probably quite a bit larger. Like your reciprocal lattice points, I should say, are quite a bit larger. So you might have to deal with more energy partials than we do in macromolecule land. But I don't really know. Yeah. So with your particular data set, were you able to integrate it? Because I have not solved that problem yet. But if you have integrated intensities, I could take a look at it at some point.
Okay.
Any other questions?
This is Ren talking here. I have a question.
Yeah.
Yeah, thanks for a talk. Very impressive. Maybe I missed it. You said the merging part actually take care of the wavelength normalization. Have you shown the wavelength normalization curve? Maybe you did. I think I missed it.
So let me address that. Yeah. So I have written versions of this code in the past that keep the wavelength normalization curve as a separate bank of variables, and when you do that, you can pull it out and look at it, and it does look quite a lot like what you get out of precognition. But the current implementation that's up on GitHub, and probably what we'll stick with going forward, doesn't explicitly deal with the wavelength as a separate curve, right? It gets dumped as a single metadatum into the neural network, so there's no real way to pull it out at the end. If that makes sense, because you're making a function that doesn't go from like R to R, it goes from RD to R2. But you could like you could make a plot that's what was the scale factor versus the wavelength, but there's going to be noise because it's considering other things like the resolution of each reflection and the P1 Miller index and things like that.
Okay,
and the
got
detector
it.
position as well. Does that make sense?
Yeah, sure.
I have a question. This is Dan Paley from LDL. Kevin, thanks for the great talk. I'm wondering how does the computational cost scale with the size of the data set?
Yeah, so right now it gets expensive once you hit around like I was just messing around with this yesterday, so I don't have like really precise numbers, but I think I recall it was around 10 million reflections or so when it starts to no longer fit in memory on a GPU on an NVIDIA Volta. So right now we've got a hard upper limit for how many reflections you can merge. In the future, what we want to do is rewrite the model in a way that we can train on subsamples of the data set. And once we figure out how to make that converge stably, it, you know, the sky's the limit. It should scale to like, I don't know, hundreds of thousands, or hundreds of millions of reflections pretty easily then.
Okay, cool. But that's interesting. So the limit you're hitting is actually about memory.
Yeah, right now. Yeah.
Uh-huh.
Because
Okay.
you know, TensorFlow has to represent all of the intermediates in the computational graph, you know, one for each reflection. So you put a big multiplier on the number of reflections
Uh-huh.
in terms of memory
Okay.
usage.
Thanks.
Yeah.
All right. Any other questions? Okay. Well, I think that's the end of the session then. Thank you, Kevin.